Ziba, and I'm here to help you out with the computational lab on Lewis acids and bases that we'll be doing in our Thursday-Friday session. And as usual, there's some preparation for you to do, having to do with setting up your lab notebook and so forth. But what I really want to talk about are the Spartan-related aspects of this work. Namely, that you'll be taking some of these molecules, ammonia and trifluoroamine and borane, and doing some calculations on them. So let's jump right straight to Spartan for that. So I've already brought up the inorganic menu here. I've got nitrogen, and I've already set up nitrogen as it would be in NH3. So there we go. And as usual, we'll go set up a calculation. We want to do it as a semi-empirical calculation. And as usual, Spartan has said, I know that that's ammonia, so should I call it ammonia? And we say, yeah, you bet. And now it's started, and hopefully it'll get finished pretty soon. And there it is. So you know all about showing the electrostatic potential mappings of these. And so I'm just, what I really want to do is focus on the energies. So let me go down here, display and properties now. And if you will look here, this far down, there's this energy. It says that the energy of that whole molecule is minus 12.83 kilojoules per mole. Good. So I want to do another one now. I'm going to construct borane, and that's B. Now, you probably know, if you've done Vesper theory on BH3, that it's a flat molecule. So I'm going to go ahead and select that. Same thing, calculations, go for a semi-empirical model. And I'm going to save it there. And it started. Hopefully it'll finish pretty soon. There it is. Now, I'm not going to bring up the energy yet because I want to look at it all together. The third molecule that you'll be making is that we want to make the adduct that results from reaction of borane with ammonia. So I'm going to make that one now, and you'll be doing this too. Now, for the because we're gonna I'm going to start back up with nitrogen. So there's, I'm going to start off with the tetrahedral nitrogen 4, because one of those will have to make a bond to the boron. So there's that. And now I'm going to go find boron. And I'll do the same thing, because I know that it's going to be BH3 and on the other side bonded to nitrogen. All right, so that looks pretty good. Now I'm going to set up a calculation. Again, that's a semi-empirical. I think everything looks okay, and I'm just going to call this my NH3BH3 adduct. And now it has started. Hopefully it'll finish pretty soon. There we go. So now I have all three of these molecules. You'll be looking at these as electrostatic potential mappings, but as I say, I want to go straight to these properties and look at the energies. And here, let's go back to your handout. Why do we want the energies? Well, it turns out to get the energy of the bond, that is the bond between the acid and the base. I've got equation 2 here, which says find the energy of the acid, the separated acid, find the energy of the base, and subtract away the energy of the adduct molecule. That's equation 2 in your handout. So that's what I will do here. Let's see the energy of the Lewis base. I see that that's minus 12.83. I see that the energy of the borane acid is 142.83. And the energy of the adduct that results is minus 38. And so when I'm going to calculate the energy of that whole molecule, I set this up in Excel, actually. Let's see if and I just set it up, because we'll want to do several calculations like this. So that's what I've typed in, is all these energies. That's the acid and the base, and this is the adduct, and we get 168. So that's what we'll That's the bond energy of NH3BH3. The one other thing that I'd like you to calculate that maybe we haven't quite done yet, but it's very, very easy to do, is I want to look at the bond distances. So there's a couple ways to do that. Right up here at the toolbar, there's a measure distance. So that's an easy way to do it. You can also go to this geometry, pop down, and get measure distance. So I'll click on that, and now I want one atom and the other atom, and as you can see, it's come up and told me the distance between them down here.